Hello everyone, we're excited to present our final projects of using the causal graph neural network to predict the accuracy of the wildfires at a seasonal scale. I'm Wen Ting and I'm here with my teammates Wenyu and Yo-Yo. Wildfires are becoming more frequent and intense due to the climate change, making it crucial to improve our ability to predict them. The seasonal scale forecasting enables the proactive disaster response, helping the firefighting agencies plan resource allocation, issue the evacuation warnings, and ultimately reduce the ecological and economic losses. Unlike the traditional forecasting, which often relies only on the local weather conditions, our work integrates the global ocean climate signals to uncover the deeper and causal relationships behind the fire events. In these projects, we implement the paper causal graph neural networks for the wildfire standard prediction published in 2024. Our goal was to replicate the paper's core findings and validate the methodology using the official ceasefire data cube. Through this, we aim to better understand the causal mechanisms behind the seasonal wildfires and explore how the ocean climate indices contributes to wildfire prediction. We will use the ceasefire cube, a global dataset for the seasonal fire modelings in the Earth systems. The dataset predicts the occurrence of the wildfires, whether a cell burns or not. It's structured as a 3D spatial temporal cube with the dimensions of time, latitude, and longitude. It spans from 2001 to 2021 in the 8 days intervals, and each voxel contains over 30 environmental and climate variables.
A dataset construction workflow, which is a crucial part of preparing our welfare prediction model. First, we begin with variable selection. The fair target variable is BASGWIS, which measures the burned area. For local environment conditions, we use the variables like temperature, precipitations, and vapor pressure deficits. We also include broader climate indicators known as OCS. We divided our data sets into training our training data sets from 2001 to 2017, tested data sets from 2017 to 2019, and validation data from 2019 to 2021. On the right, you can see the sample area, which is a cropped region over Europe between 25 and 75 and latitude and 15W to 45 longitude. Next.
I would like to give an overview of our model architecture. First, all the input data were passed into a one-layer LSTM to capture the node's temporal features. At the same time, an adjacency matrix is calculated to capture the causal relationship among the variables, and it's derived by the PCMCI algorithm. And then the features were multiplied with the adjacency matrix and then passed into a two-layer graph convolutional network to capture more features through nonlinear transformation. And then the final predictions were generated through graph pooling and a binary linear classifier and then we calculate the prediction confidence with softmax. Next. The evaluation matrix we used are identical to the paper, the AUROC and the AUPRC, which are a proper evaluation matrix for such wildfire prediction models. Next. Sadly, we want to be as transparent as possible. Despite our ablations, we did not reach the performance that we expected. However, we recently realized we came to a late realization that we improperly processed the temporal inputs with different time intervals and did not pad them or linear interpolate them correctly, which significantly affected the model performance, and the placement of the ground truth on the time horizon was also a little bit off. So we are still doing ongoing corrections and ablations to correct this issue. Next. Despite all that, we believe that the graphic neural network would contribute significantly to the wildfire prediction, capturing the lot of very unpredictable patterns among various variables, especially in the Earth system and climate domain. And we believe that it could adapt to a variety of tasks in this domain. Thank you very much.